So this is our week 8 discussion, as I said. We're going to try, no, I will get through 6 problems unless there's some technical difficulty which may occur. But these 6 problems will, from last week at least, we'll come back to the concept of streamline functions. And this week, we're going to introduce the topic of velocity potentials. So I guess that's like the new part from this week. And we're going to solve some more problems related to those concepts. So let's talk about streamlines first. In this problem, we're given a streamline for this. We're given the streamline function for for a family of streamlines in this flow field. Just one thing quickly note: why the streamline is so nice is velocity field is usually a vector, so it's like 2 components, right? But with the streamline function, we can basically store the information of those components, those 2 components with different functions, into one function itself. That's why the streamline is really nice. So here we see that our streamline function is represented in terms of, or with the variables of lowercase r and theta. Lowercase r refers to its radical location in the free field, so like how far you are from the origin, and theta refers to the angle, the directionality of that radius in which you are far from your origin. And this is equal to u sine lowercase r minus uppercase r squared over lowercase r. The thing about the psi is what makes this a family function. Substituting in different arbitrary values for psi then gives you different streamline plots, which are basically different paths in which fluid particles can travel through of your flow field. So therefore, left-hand side is going to be a constant in the end. So what I want to do is I want to move all my variables to the left-hand side. I want to store all my constants on the left-hand side. So from here, I see that I can factor out an uppercase r. I should probably put a sign thing there. And that's equal to psi. I'm going to isolate my constants over, as I said previously. Therefore, I'm left with just sine angle times. So here we see lowercase r over uppercase r minus uppercase r over lowercase r. I'm going to term this term eta, and eta is going to refer to lowercase r over uppercase r. I've basically non-dimensionalized how far, like my radical position. So essentially, if eta is 1, I am basically sitting on this I'm sitting on the surface of a circle. If eta is greater than 1, I'm basically moving away from this circle. Eta less than 1 refers to I'm within this circle. And I'll get to the circle part in a bit. Now I have a function, or basically, I have basically all my constants on the left-hand side equal to sine theta multiplied by a function of etas. So, as I said earlier, we're working with family of functions. To obtain one function from the family, we're going to substitute in a constant for psi. And so left-hand side, let's group it all up. If I let my left-hand side equal to positive 1, I could then subsequently, in order to plot this streamline, I let my theta be equal to like 0 degrees, 10 degrees, 20 degrees, all the way till I get around the entire polar plot. And then I find the corresponding eta values. Eta, I think it should be 2 values, but eta could equal to like eta 1, eta 2, or I guess eta naught, eta 1, eta 2. I get corresponding eta values. And with these 2 terms, I can essentially get this following image here. I can plot it. So as I said earlier, let's say for eta 10, eta 10, eta 20, eta 30, etc. I get the corresponding r values, or I guess eta, which are r values, that correspond to one streamline. And with all those points I plot down, I can draw a line through it and obtain my streamline. Any questions on this concept? Okay. But if not, that is the one kind of like a refresher on streamlines. Let's go to the next problem. So next problem, now we're going to talk about velocity potential. So we talked about streamline as a family function. That's like the path for the fluid particle. At least for now, just think of velocity potential as something similar to the streamline function. You are basically able to store the information of all the velocity components within one function. Velocity potential, also known as phi, it serves a similar purpose. So, let me talk about this now. In regards to solving for streamlines, a streamline function I should specify, there's a process we usually go through, and you'll be seeing this discussion. For streamlines, usually first thing you want to do is you want to prove its existence, and to prove its existence, you take the divergence of the velocity field. The divergence, essentially you're looking at a dot product, and it's a dot product between del operator and your vector v. And maybe just for a note, del, you can think of it as a vector of your partial derivatives. And v is the vector of its three components. So this del, this is v. Dot product gives us the following. One second. I want to put this down. So dot product gives us the following. If this dot product is equal to 0, this implies, first of all, for an incompressible flow field, this implies that our flow field is continuous. Solving this equation gives us satisfies the continuity equation, therefore we have a continuous flow field. This is discussed more from last week's discussion. But that's the dot product. We prove that flow is continuous. Therefore, your streamline does exist. That's the train, the process. And I think I wrote on the whiteboard too. Divergence theorem, which is dot product, equal to 0, means we have an incompressible continuous flow field. Therefore, psi exists. In regards to phi, we use a new tool, which I'll discuss more today. We take the curl of our velocity flow field. Curl is a cross product. So it's a little messy, but essentially, if you were to take a cross product, you get the following matrix slash determinant, but it looks something like this. And for each of the I, j, k components, we can solve for the associated determinant and get the following form. For I, it'd be dw of dy minus dv of dz. For j, we're looking at du dz minus dw dx. And the last one is dv dx minus du dy. And this curl is referred to as vorticity. I don't think I proved it right, but it's vorticity. These terms are vorticity terms, and they refer to basically the vorticity value itself refers to the rotation of fluid elements. So if you have a fluid element and you have vorticity, the fluid element itself is going to be rotating around its own axis, essentially. It's rotating around its own axis. In this class, I believe, most of the time, we want this term to be equal to 0. Because if this is equal to 0, we have an irrotational flow field. And this is good because irrotational flow field proves that our velocity potential does in fact exist. Oh, sorry, yeah. So, just a brief reminder, for streamlines, divergence theorem, which is dot product results in satisfying the continuity equation for an incompressible flow field, which then implies that streamlines do exist. For velocity potentials, we do the curl of velocity field, and then the curl of velocity field proves, if it's equal to 0, proves an irrotational flow field, which proves that phi exists. Yes?
If it's not incompressible, can you not do the divergence of it to see if it's 0, or does it not apply?
Yes, I believe it's important because the actual formula for continuity is d psi dt plus essentially the dot product of this. So if psi is not constant, you can't get rid of the steady unsteady term. You also have like your divergence theorem is a little more messy. That's why, in order to at least go through this process of just simply taking dot product, we have to imply that density is constant, which then spits out this following term.
I see. Thank you.
Yeah, no worries. But otherwise, you can just technically solve this equation here to prove continuity if you have a compressible flow field. Okay. We want to solve for velocity potential, given this function up here. So let me solve for that. I have u and v. The relationship between, once again, as I stated earlier, phi, and psi are able to store both velocity components as one function. That's what makes it a very powerful tool. U is equal to the derivative of phi respects to x. V is equal to the derivative of phi respects to y. So taking the partial derivative of your velocity potential, you can reobtain your u component and your v component. So therefore, to get psi, we're going to do separation of variables. So u, we saw, was given on top, but I'll write down here, is equal to a times x squared minus y squared. Separation of variables, give me d psi is equal to a x squared minus y squared dx. Take integral of both sides. I get that phi is equal to integral of x squared, that's x to the power of 3 over 3. Y squared is a constant, so just add x to it. And here's the thing. I'm going to add it with my constant with respects to y. The reason being is, the reason being is if I take the x derivative of phi to return to my u component, this term, or these two terms, first, would come back to its original form of a times x squared minus y squared. And this last term, x derivative of a y-based function is going to give me 0. So then it'll go away and I return back to my u component. That's why I have this constant with respect to y. So we have partially solved for phi. Reason being is we've only basically considered the u component of it. Based on the u component that we have, we got a corresponding phi function. But as I said earlier, phi should account for both u and v. So we have to do a comparison test to v and basically see, do we have the full answer or just part of our answer? And I'll show that as the following. As I said earlier, v is equal to the partial derivative of phi respects to y. Therefore, if I take the partial derivative of phi with respect to y, what do I get? I get that this first term here, x to the power of 3 as a constant, goes away. Minus xy squared, that would give me minus 2xy, times my constant of a, I forgot about that, plus c prime of y, because I derived with respects to y, so c prime of y. And this is all equal to v. V being, I think it's up there earlier, but it should be negative 2axy. Shown right here. These two terms we see two equivalent terms, 2xya or 2axy. These terms cancel out. You're left with, or I'm left with, c prime of y is equal to 0. My solution is a x to the power of 3 over 3 minus xy squared plus cy. I need that cy term to complete my answer. So to obtain cy, integrate both sides. Integral of 0 is just 0, but because it's a general integral, I'm left with a constant. A numerical constant, not a function constant, a variable constant, which I then plug back into here. Because phi is like similar concept to like the streamlines, because phi is going to essentially already be a constant when I plug in arbitrary values for it, we just move this constant to the left-hand side and combine those both to be called as phi. So final answer, phi is equal to a times x to the power of 3 over 3 minus xy squared. Any questions on the math part of it? Okay, if not, let me show this as well. So if I were to plot my phi functions based on different arbitrary values, as I said earlier, I let phi equal like a or 2a or 0 or something like that, I get these blue lines here. So those are my phi values. and they're in blue. And these phi values, the way I see it, it's kind of like, I think it's called streak lines or something. There's like lotus points. It was one of those two terms. But in a way, you can imagine it as their checkpoint for fluid particles. And here's what I mean by that. Phi values are, one of their properties, what makes them unique, is they are perpendicular to streamlines. So these dotted lines are your streamlines here. And as you see, these streamlines, they're actually, if you take like the dot product of that specific point, they are perpendicular to your, the green lines are perpendicular to the blue lines. Your streamlines and your velocity potentials, they are perpendicular. And I believe this is how it works. So we track a set of fluid points at one velocity potential. They should move together and reach the next velocity potential together. So that's what the velocity potentials are. The points on the streamline that are moving down, fluid particles moving down the streamline, should cross their respective velocity potentials together as a unit as you move through the flow field. So that's the importance, or that's kind of like the unique characteristics of velocity potentials. Any question on what I just said? In the end, though, both terms are basically utilized to store the velocity components information, but when you plot them, that's their relationship, that's their characteristics. One is streamlines, which is the path which a fluid particle follows through. The other is kind of like checkpoints for which fluid particles cross together. They march together through the potentials. Okay. Just one last, I guess, quickly. Because I think I visualize it better like this, but I have streamlines going this way, and I should have my potentials being perpendicular to it, and fluid particles cross together through that streamline. Okay. Next problem. So here we are looking at flow through a pipe. This is, I think, Poisson-Newton's flow. And it's the figure B. Essentially, it's flow through a pipe. We have our maximum velocity at a center line being denoted by the origin with this coordinate system. And as we move towards the walls of the pipe, we see that due to the no-slip condition, our velocity drops to 0. Therefore, our velocity profile is described as the following. Velocity profile is c times h squared minus y squared, where c refers to the max velocity at the center line divided by 2h. Therefore, when I plug in y0, I would return back u max, or u center line. Okay, so what we're interested in is A, finding the streamline function, and B, find the formula for the streamline function. So A, streamline function, we want to determine if it exists. So as I stated earlier, we go through this process. To prove that psi exists, first what we do is divergence. We check the divergence, which is basically just the dot product. So, partial derivative of u with respect to x, plus partial derivative of v with respect to y, plus partial derivative of w with respect to z, should equal to 0. We're working with a one-dimensional flow, just a u component, so these two terms cancel out. And I'm left with the partial derivative of x of c h squared minus y squared. There are no x terms in this function, therefore, that divergence checks out. The divergence equals 0. This checks out because basically what it implies is, concerning the flow is an inexpressible flow field, we can prove that the flow field is also continuous, which then implies that your streamlines do in fact exist, based on that process. So, now because it exists, we're interested in finding the streamline formula. So, one thing to note, at least for u, let's start with u first. Earlier, we saw that u is the partial derivative of phi respects to x. Because your streamline is perpendicular to that, what you'll see is that psi, or u, is partial derivative of psi with respect to dy. Once again, it's partially due to the fact that they are perpendicular to each other. We changed the term. Therefore, u is equal to c times h squared minus y squared. We're going to do separation of variables. The psi is equal to c times h squared minus y squared dy. Integrate both sides. I get the psi is equal to c times integral of h squared, that's a constant, so that becomes h squared y. Negative y squared, integral of that is negative y to the power of 3 divided by 3, plus a numerical constant. Because we're working 1D, integral should just give you a numerical constant. If you're working in 2D, you will get back a constant that could be a function of another variable. But once again, constant, or psi, we will plug in a constant for it when we solve for streamlines. So we just move this constant over into this left-hand side and combine it into just one psi.
Can you scroll up a little?
Oh, yeah. Okay, any questions on the math? Only thing I'll point out is one thing that's kind of unique is when I solve for psi of 0, I'll see that the center line has psi of 0, but there's also two other points where psi is equal to 0. And then I have psi, I believe, at the top, less than 0, and greater than 0, less than 0, greater than 0. So we get some kind of, I guess, function where the psi value is changing. But overall, in the end, when you solve for psi, all that matters is for certain values, you'll get streamlines associated with them. Yes?
Why did we get rid of the constant?
Yes, because the whole point of the streamline function is we're plugging. Streamline function is a family of functions, right? So for psi, in order to obtain one streamline in that family of functions, we plug in a constant for psi, right? In order to get associated streamline with it. So in a way, it's like a constant on one side and another constant. So we just combine it to be one constant. We describe it as just one constant.
Okay.
Yeah. Maybe let's try better, which is like I subtract both sides by the constant. But in the end, because the whole point of streamline function is psi is going to be a constant, that's just a constant. Okay. All right. If there's no other questions, let's move to the next problem. So previously, we worked with the Poisson-Newton's flow through a pipe, parabolic velocity profile. Now we're looking at linear Coulombet flow, where we have a fixed plate and a moving plate, and therefore we get like a linear distribution for velocity. Now here, we're interested in proving that this Coulombet flow has a streamline function, but no velocity potential. So once again, how do we prove that? It's what we did earlier in the last two problems. Let's start with psi. So psi, we start with the divergence theorem, which is the dot product. That's how I visualize it. It's a dot product. So dot product of the divergence is du dx plus dv dy plus dw dx. Once again, summation of your partial derivatives with respect to their velocity components. And it should equal 0. That's what we're hoping for. I forgot to mention, for this linear Coulombet flow, you've seen it in class before, but essentially your velocity profile with respect to y is the following. It's the slope, which is in rate of change. So change in velocity divided by change in distance, which is height of between the fixed plate and moving plate, multiplied by y. So that is the description or relationship between your velocity profile and your y location. So this is another 1D flow. These two terms get canceled out. We're left with the partial derivative of x of v over hy. There's no x terms involved here. This whole thing becomes 0. This is true. Once again, we've proven that we have an incompressible flow field. That for an incompressible flow field, we have achieved continuity, which then implies that psi does exist. Psi being streamline. Streamline exists. They have very similar sounding names, but psi exists. We can solve for it, which I guess I'll do really quickly. So u equal to d psi over dy. D psi is equal to u, which is v over hy dy. Integrate both sides, I get the psi is equal to v over y squared over 2, plus numerical constant, which then just goes away. So yeah, once again, the main point is though, we've proved that the streamline does exist for Coulombet flow. And that makes sense. Like, look at these lines. You see these streamlines going from at the fixed plates, growing larger as you go to the moving plate. Streamlines do exist. We can prove that. We can also visualize it too, is what I'm saying. Now, they want to talk about the velocity potential now. Velocity potential, once again, we work with curl. which is a cross product. Let me specify that over here too. So, as you saw earlier, the cross product is not, the dot product returns a scalar value, but the cross product returns a vector, I guess, answer. We're working with 1D flow. So therefore, in regards to this cross product, in a 1D flow, the top two terms are going to cancel out. There's no z component, there's no w's. These top two are going to cancel out. But this last component, it's present for a 2D flow field. So we're going to take that last one. So cross product, in the end, is just, I guess we get vorticity, which refers to the rotation of a fluid particle of x, y, and z. But these two we know are equal to 0. This one we don't know. This one is dv over dx minus du over dy. There is no v component. We're working 1D flow. This term goes away. The last term, though, we're looking at d of dy of u being v over h times y. Derivative of this, there is a y component, so we're left with the slope, as I said earlier, v over h, which is not equal to 0. Therefore, we have a rotational flow field, which implies that velocity potential does not exist. And so, basically, you can have one, or you can have both exist, but you also have cases where only one exists and not the other. And in this case, the reason being is, earlier, I think maybe 2 problems ago, I was discussing how you can visualize the velocity potential as checkpoints for fluid particles moving through the flow, and streamlines are after the path which they follow through. So in this example here, here's one example of the velocity potential. Here's one checkpoint. The flow is moving through the flow field, I guess as a fluid particle is moving through the flow field, there's a checkpoint here. But at the bottom we have a fixed plate. Velocity, there's no particles moving there. At the moving plate, velocity is going to keep moving. Therefore, the following checkpoint is going to look like this, then this, then this, and this. And as it keeps skewing because the fixed location is not moving. And at some point, it's basically your checkpoint, your potential, quote unquote, is going to be almost basically parallel to this fixed plate, and there's no function that can describe that. Therefore, there's a curl, there's going to be rotational effects occurring in the flow field. Your velocity potential, your psi, does not exist. Any questions about that? Okay. If not, let's go to the next problem. Actually, no. I'm going to quickly go to this one. I'm going to quickly through. We want to basically find stream function velocity potential. I'm going through this quickly. Streamline psi. Once again, it's the divergence. It's the dot product. Is this? It's x derivative of u plus y derivative of v plus z derivative of w. We have no w term. That goes away. So x derivative of 2v x over L minus y over L plus y derivative of negative 2v y over L. X derivative of x over L, that's 1 over L, multiply the constant of 2v over L. X derivative of y, 0. Y derivative of y over L, that's 1 over L, times the constant negative 2v. I get negative 2v over L. These two terms cancel out. I get 0. Once again, what does this imply? For an incompressible flow field, this is our assumption, we have a continuous flow field. Therefore, psi does exist. I'm going to solve for psi. It's similar to, I think this is similar to the second problem we did this week, of this recording. U is equal to d psi of d y. U is 2v times x over L minus y over L. Separation of variables. Integrate both sides. Psi is equal to integral of x over L, that is 2x over L. X squared, nope, I'm blanking, sorry. Y, the integral with respect to y of x over L, that is xy over L. Integral for negative y over L, that's negative y squared over 2L, plus a constant with respect to x. We can also, or we have part of the answer for psi. Psi is derived with the information of u, but it's a 2D flow field. We also got to factor in the information due to v. So, one thing to note, as I said earlier, for velocity potential phi, you see here for the u, they changed the x, the x and y component. Same thing for the v. So for psi, it'd be d psi dy, but for the streamlines, it is negative d psi dx. So let's derive psi with respect to x. 2v, or sorry, x y over L, that derivative of x just gives me y over L. Y squared over 2L, derived with respect to x, that gives me 0. And I have c prime of x. And this is all equal to negative v. V is negative 2v y over L. So therefore I get positive 2v y over L. Similar to before, we see these two terms cancel out. C prime of x is equal to 0. We need c of x in order to plug back into our original equation. Integrate both sides. C of x is equal to a numerical constant. Therefore, psi is equal to 2v x y over L minus x squared over 2L plus numerical constant. We subtract both sides by the numerical constant, and we're left with just psi is equal to that term. So that's the solution for the streamline function. Let's go talk about the velocity potential. Velocity potential, we are doing the curl. We're doing the curl. Curl, which is a cross product. So cross. Same concept as that Couette flow. We're just looking at the last term because this is a 2D flow field, one dimensional or two-dimensional flow field. We just look at the last term. dv dx minus du dy. At some point, if you do enough, you might just memorize it. So the x derivative of v, negative 2v y over L minus the y derivative of u being 2v times x over L minus y over L. We see that this term cancels out, but the remaining term, we actually obtain negative 2v over L. This is not equal to 0. Therefore, we are working with a rotational flow field. And once again, we see that psi does not exist. Any questions on that, I guess, flow field? Okay. Not, I'll keep the answer, like part of the answer here, but I'm gonna quickly move on to this next part. So in this question, what we're given is, it's kind of like in reverse now. We're given the phi value. We're given the velocity potential for some two-dimensional incompressible flow field. So already, because we're given the phi value, it implies that we have an irrotational flow field. Just heads up. Okay. So in part A, we want to figure out if it's true that the second, so essentially, they're asking if the Laplacian of phi is equal to 0. That's the first term. And if so, what does that mean? So the Laplacian is just the del operator squared applied to phi. And you think of it as, it's kind of like a double dot product. The way I see it is, it's del operator dot del phi, which del phi is really a dot product itself. So when you do this, what you actually obtain is you get, it's just a second order of the divergence. It's kind of like a second order of the divergence. It's d squared of phi, with respect to dx squared, plus d squared of phi dy squared, plus d squared of phi dz squared. And I think, hopefully, you can see similarities between this and the divergence theorem from earlier. And speaking of the divergence theorem from earlier, we can further simplify this, or we can further simplify this expression if we wanted to. And one way to do that is we remember our relationships with respects to phi and velocity components. Because once again, phi contains the two velocity components in and of itself as one function. Also quickly, this is a 2D flow field, so we're going to neglect the last term. There's no z component. U is equal to d phi dx. V is equal to d phi dy. That's the relationship between phi and u and v. If we were to rewrite this expression here, you can see that it's actually d dx applied to d phi dx plus d dy applied to d phi dy. So in a way, we can rewrite this expression as du dx plus dv dy equals 0. And what this is this is just that part of the continuity equation. So essentially, solving, or if the Laplacian of phi is equal to 0, you can basically showcase that for an incompressible flow field, we can achieve continuity. Because this term here, del dot product of the velocity flow field, is equal to 0, which would imply continuity. So, if we prove this, flow field is also continuous. Not only is it irrotational, because we already know that, it's also continuous. Okay. So, backtracking a bit to the first equation, so backtracking to these two terms here, we can solve for u. U is the x derivative of phi, xy plus x squared minus y squared. X derivative of xy, that gives me y. X derivative of x squared, that's 2x. X derivative of y squared, that's 0. And for v is the y derivative of phi. Y derivative of xy, that's x. Y derivative of x squared, that's 0. Y derivative of negative y squared, that's negative 2y. So we have our u and v components. So therefore, the Laplacian of phi is equal to x, the partial derivative of x applied to u, which is y plus 2x, plus the partial derivative of y applied to v, x minus 2y. X derivative of y, 0. X derivative of 2x, that's 2. Y derivative of x, that's 0. Y derivative of negative 2y, that's negative 2. And as a result, I see that the Laplacian of phi is equal to 0. Therefore, not only do we have an irrotational flow field, we also have a continuous flow field. So that's what we've proved by going through this process. I think part B is, does a streamline function exist? As I discussed earlier, we have continuity. Therefore, phi does exist. And I think part C is solving for the streamline function. That's the last step. Okay. And technically part B. So in part C, we're now trying to find the streamline function, and it's a very similar process to what we've been doing this whole time. So, once again, stating that u, partial derivative of psi with respects to y, u is given as y plus 2x. We're going to do separation of variables. D psi is equal to y plus 2x times dy. Integrate both sides. I get psi equal to integral of y with respect to y. That is y squared over 2. Integral of 2x, that's a constant, with respect to y. It's going to be 2xy. Plus a constant with respect to x. Because once again, taking the y derivative of phi will return us back to u, because c of x derive with respect to y, go away. So now we have the u component factored into our solution. But how about the v component? Let's factor in the v component into our solution now. So we know that v is equal to negative partial derivative of psi with respects to x. So therefore, I'm going to derive psi with respects to x. First term, y squared over 2, that's going to be 0. Second term, 2xy, derived with respect to x, that gives me 2y. Plus c prime of x. and this is equal to negative y. Y is as shown above, right there, x minus 2y. So we have negative of x minus 2y. You'll see that we do have a cancellation. We see that this 2y term is already accounted for. We don't gotta worry about that. But there's this negative x term that we have not accounted for yet from the v solution. That's new. We get c prime is equal to negative x. To obtain c, which is part of our solution for psi, integrate both sides, we get that cx is equal to negative x squared over 2 plus a numerical constant from the general integral. We're going to plug this back in here. Therefore, final solution is psi equal to y squared over 2 plus 2xy minus x squared over 2 plus numerical constant, which we can cancel out because psi is going to be a numerical constant itself. So this case is a little more unique because both your u and v components have like unique solutions that have to be accounted for in your streamline function. That's why it's important to count across, to check all components and factor them all in. And yeah, that's the final solution for a streamline function. Any questions about that? If not, last problem and we're done. Okay. So here it says we're looking back at case B, which is the flow through a pipe, Poisson-Hurley's flow. And here, I'm going to basically write down the equation for this. It's y. This is pipe flow once again. It is u max multiplied by 1 minus y squared over h squared. In essence. So part A, we want to solve for wall shear stress, that is tau of W. We learned in class that tau of W is equal to, for Newtonian fluids, viscosity mu multiplied by du dy, which represents strain, but at least in 2D, you also have a dv over dx term, if it were 2D. We're not, fortunately, so we can cancel that second term, but if it were 2D, that's actually something to consider. Okay. So wall shear stress. So shear stress in general is equal to that equation. The y derivative of u gives me the following. U max 1 minus y squared over h squared. I get mu times y derivative of y squared over h squared. That's 2y over h squared. Multiply my constant u max. I then get negative u max times 2y over h squared. Wall shear stress. Wall shear stress is when you evaluate shear stress at a wall, which is y equals plus minus h, because our origin is at the center line. So evaluating at plus minus h for y, I get the following. I get mu multiplied by u max times 2 times plus minus y divided by plus minus h divided by y squared. Therefore, I get mu times u max times plus and minus 2 over h. So that is the strength or value of the shear stress at the wall. Part B, compute the stream function. We did this in the last problem, or like when we look at this problem, so I'll quickly write it out. Basically, 1D flow, so u equals partial derivative of psi respects to y. Psi, just take the integral with respect to y. You're going to get u max times y minus y to the power of 3 divided by 3h squared. Plus some kind of constant, which then goes away. Okay, C, vorticity. I think we actually did not talk about vorticity for the pipe flow, actually. We talked about it for the wet flow, but how about pipe flow? Once again, vorticity refers to the curl, which is cross product. If I break it up, we have the x, y, z terms, which would be the following. Next term, it would be u with respect to z minus z with respect to x. And then last term is this one. Once again, this is based on that cross product matrix determinant thing I was talking about like back in the first problem or second problem. But you get these terms here. We only got u. We're only working with u and y. There's no x, y, there's no v, there's no w. So these two terms are going to equal 0. But the last term, let's check it out. We have dx of v, which I guess is also 0, minus dy of u being u max, times 1 minus y squared over h squared. There is a y component here. That derivative is going to give me negative u max times 1 minus 2y over h squared. This is not equal to 0. Therefore, vorticity, I think they asked for what is vorticity. Vorticity of z is equal to the following. Vorticity of x and y equals 0, which is nice, but the vorticity of z is equal to this formula here. Velocity potential. Because this term is not equal to 0, we have a rotational flow field. And therefore, according to part D, which asks to find the stream function, velocity potential function, phi does not exist. And is due to this process. Last part, E. E asks us to solve for average velocity. So, obviously, we're working with a parabolic velocity distribution, so velocities at different locations get different velocities. To solve for the average velocity, we can integrate via the following. You do 1 over a times integral of v, or your velocity distribution, times dA. So it's basically saying, looking at the cross-section of the pipe, we want to solve for the u velocity coming through that cross-section at each point in that cross-section area, and then divide by that area to get the average, essentially. But u is only with respect to y. We're looking at a 1D flow field. So you have to convert our cross-sectional area terms to just a cross-sectional width, or cross-sectional like height, essentially. And we can do this if we assume that in this flow here, there is a width w, and if in this width w, the parabolic velocity profile is the same across this entire width. And so, doing so gives the following, which is area is then the height times the width, which gives you cross-sectional area. If that's w, 2h is on the vertical side. So I get 2h times w times the integral of u of y, which is u max, times 1 minus y squared over h squared, multiplied by w times dy. So these two w's cancel out. And we're integrating u of y with respect to d of y, right? So essentially, we're looking at this. This should look familiar because essentially what you're doing is this. So I guess fun enough, when in this format, solving for average velocity actually ends up being similar to solving for the streamline. And we have solved for the streamline before. We have the solution for that up here. And I should have mentioned, we're evaluating with the bounds of negative h to positive h, which is the bottom surface of the fixed wall to the top surface of the fixed wall. So this results in 1 over 2h multiplied by this term here, evaluated from negative h to positive h. One over 2h multiplied by max times, I said that, h minus h to the power of 3 over 3h squared minus negative h minus negative h to the power of 3 divided by 3h squared. U max, 2h multiplied by 2h, these two combined, negative h to the power of negative h to the power of 3 divided by 3h squared, minus h to the power of 3 over 3h squared. So everything's kind of like, I think, times 2. This to the power of 3 cancels to the power of 2. I'm left with u max times h over h to the power of 2 times h multiplied by 2h minus 2h over 3. I believe my math should check out, but these two h's cancel out. I'm left with u max times 1 minus 1/3. My final answer is the average velocity flowing through the pipe is 2 over 3 times u max. Sorry. And that's solution for part E. And that's the entire problem. Any questions on everything I went through? If not, that's the end of my discussion. Have a good day.